Combustion day is a special day. We get to burn a lot of stuff. But I like to think of it as burning for learning. There's a reason we do combustion day. And it's so that you know how to verify a combustion reaction. And you know how a combustion reaction works. So first of all, you want to think about a combustion reaction is always a hydrocarbon burning in the presence of what? Yeah, you've known this from a very early age. You need oxygen in order to burn things, right? And then it yields CO2 and H2O. So we should be able to see some of this stuff, or at least predict it and see some of the effects of all these pieces, having the hydrocarbon, having the oxygen, giving off CO2 and H2O. So keep that in mind. Combustion reactions are really nice because they're always the same. Hydrocarbon plus oxygen gives you CO2 and H2O. Always. Always, always. So one of the things that you're going to struggle with is that what is the difference between when something's heated? Well, heated usually means decomposition, but when you see the verb burns, you're thinking combustion here. And that's going to be actually more specific, obviously. Burning means it requires oxygen, and it's a hydrocarbon burning here too. All right, so let's kick it off first of all. I have that other hydrogen balloon, so let's get going. Now you have a little bit of warning. Are you ready, Sammy? Okay, so here we go. Ah, this one's bigger too. Okay, ready? Nice. It's a nice combustion reaction, right? No. This is not a combustion reaction, actually. What type of reaction is that? It's not a decomposition reaction. It's a synthesis reaction. What was I combining? Hydrogen and oxygen in the air. The room is a little bit more watery. That's not really anything that we can, pick up because obviously there's not much there. That's technically not a combustion reaction. There's a combustion reaction right there. You have to have the hydrocarbon, and that was just hydrogen and oxygen. You might hear it called combustion, but in the definition that we're using, a hydrocarbon burning in the presence of oxygen, that's not what it is. Technically, the hydrogen balloon popping or burning that way is moreover the synthesis reaction to form water. But enough with that. Let's get to real combustion, right? Okay, so we're going to start off with propanol. And propanol, first of all, you probably recognize it more as isopropyl alcohol. And it is a type of propanol. Iso just is a way that we're going to identify an organic molecule. We're not going to worry about that, but we're simply just going to experience it. What? What? What are you talking about? So, now we're going to be a little bit more dramatic with the match, right? Like, no! Okay, and there we go. Now, it actually doesn't burn as easily because there's a little bit of water in there, but still, I think that's pretty amazing. Now, first of all, this is the most obvious thing for a combustion reaction. What do you notice? Fire. Fire, right? So when you're actually, this is one of the neatest things about a combustion reaction is the fire part of it, because it is so easy to identify the verification. There's going to be fire. Can you listen to the acoustics there? Yeah. Yeah, that's the carbon dioxide that's building up. You can it changes some of the acoustics in the room. It's like a little bit more echoey. Yeah. Yeah, you can hear it there. So but the biggest thing is that you can feel the heat, you can see the light, definitely fire. So that is one verification, but that's not the only thing. So we'll keep that in mind as we're going through. All right. Now, I dropped a few matches, so I'm going to pick those up, put those off to the side here. And so that is obviously the first part of combustion day that we want to tackle. Now, okay. The other thing that I want you to notice is take a look at this. Now, we're using propanol. It's not exactly isopropyl alcohol, but for our purposes, it's good enough. Propanol has that little OL on the end. Do you remember what that means? Well, how is it different than propane? It has an oxygen. And that's not just an oxygen. It has the OH on it. And the OH makes it what? No, okay, this is for organic molecules. When we have an OH on inorganic molecules, then it's a base. An OH in this situation makes it what? Think back to van der Waals forces. Would you classify this molecule as polar or nonpolar? Polar. And the reason is that OH makes it polar, and therefore makes it sticky, hence a liquid at room temperature. So think back to van der Waals forces and why things are liquids versus gases, and this is one of those reasons. The polarity of it simply makes this a liquid at room temperature. So do we have the alternate? Of course we do. We have my favorite type of pane, propane. I don't think there's any other type of pane that's nice too. But propane obviously is a gas at room temperature, okay? And take a look at it. Is there any polarity to this molecule? No, not really. So this is C3H8. It's nonpolar, and because it's nonpolar, it's a gas at room temperature. Now that's not the only cool thing about propane. Propane is also more dense than air. So you can do this neat trick with it. Now, just for verification. Got to get all of it out, you know. Okay. Because it's more dense than air, it's going to sink down into the lowest space that it can contain. And there we go. So because of its density, it actually does this. Which you think, pretty cool, right? No, not really. Because if you have a propane leak, which we really call natural gas, what is it going to do? Sink. It's not like methane. If you had methane, it's going to disperse. If we had like a methane leak, it's not that horrible because you could just simply open a window and it would disperse. It disperses outwards. A heavier gas like propane sinks, and that's a little bit more dangerous there. But that's one part there. Now I told you that we'd also take a look at some of the characteristics there. All right, well let's see how it does with oxygen. So for instance, I can control the amount of oxygen, and this is actually done quite a bit in engineering. If you want to control where combustion is taking place. So if I want to control where combustion is taking place, I simply have to basically point where the oxygen is going to react with it. And it's going to happen right here. So this is where the oxygen is coming out of. Notice it's not going up into the tube because there's really no oxygen there. And so that's a pretty simple kind of thing to see. We definitely need oxygen for combustion to happen. But again, like an engineering situation, I can also control the rate at which this is reacting with oxygen. Now that's just reacting with oxygen on the outside. You can smell the rubber, can't you? Yeah, that's just the burn or the rubber stopper. Okay, so if I want to control the amount of oxygen or the rate at which it reacts with the oxygen, I simply have to propel it. And there you go. So obviously that's going to react at a much faster rate by just doing that itself. So definitely you have to have oxygen in order for that reaction to happen. All right, so which one's next? Ethanol. Where have you heard about ethanol lately?
Gasoline.
Yeah, gasoline as an additive or even a substitute, an alternative fuel. And the reason is that when you have ethanol, first of all, it's an OH, so meaning it's polar, it's an alcohol, and it's going to be liquid at room temperature. We don't have ethane to show you, but you could predict ethane would be what? Nonpolar, so a gas probably, right? Okay, so what we can do is take a look at the power of this. And again, if you have an internal combustion engine, you're going to control where combustion is taking place. So we'll just add a little bit of the ethanol here. Don't need much. Okay, I'm going to basically consider this as like my internal combustion engine. And what happens in internal combustion is that you start the combustion reaction happening, and in the combustion chamber, it's going to produce gases that expand rapidly. And if you're in an engine, those gases are going to push, pistons forward, etc. In this case, it's not going to do that. It's just going to move a ping pong ball. So what I can do is I can control where combustion takes place. Right now, there's enough oxygen. So there we go. Pretty impressive, right? Okay. And so if you notice, there was just a little bit of ethanol in there. So there's a lot of energy trapped in that molecule. All right. So, well, let's try it once more and see what happens. Okay. More isn't always better here. And I don't mean that in the case that it's not always going to give us a bigger reaction. Sometimes it won't even work at all. Now, we're going to try this again, and we may not get as good of results. Watch. Oh, there. See, that wasn't as good, was it? Why? There wasn't as much oxygen. Because what had happened is that it produced carbon dioxide within the bulb here. And so because there wasn't as much oxygen, the reaction didn't happen as quickly or as much as it did before. In that case, oxygen is the limiting factor. Now think about that. If you're driving a car and you have a clogged air filter, what's going to happen? You're not going to have as much, you're going to have a worse gas mileage, right? And that's because you have to get enough oxygen in to make the reaction happen at a better rate or more efficient rate. So there is your ethanol.